That's a retinal detachment. Can we turn that light off, if that's possible? This is the retina, the wallpaper coming off the wall. You can see the cotton wool patch in the same eye. And deep to this is the retinal pigment epithelium. This is the optic nerve that carries the message back to the brain. These are the retinal vessels. And this is a new technology. Now, we also have some other really kind of amazing technologies. You'll recognize a histological section. I wanted to honor Dr. Goodluck in the PATH department for inviting me today. And so here's a H&E of the macula, the foveal depression. Here's the RPE overlying the choriocapillaris. It's a non-synaptic layer. And here is another section, and they are labeled with the interlimiting membrane and nerve fiber layer, and down all the way to the photoreceptors, the outer nuclear layer, the IS-OS junction there, and here's the RPE. Well, we have a way of taking this, getting a section just like this, optically, in you, while you're alive, and it takes about 3 minutes to do. It's called an OCT. And this is an OCT in one of our patients. And you can see all the different layers that I just listed there. And so here's the RPE. And we can get a pretty good look at the RPE, whether it's there or not. So it's a really spectacular imaging device. Not only that, these OCT devices have tracking that yields something called registration. So we can go back to the same spot in the macula later on and look at it again precisely. So we have a really accurate way of looking at these cells. Not only that, the room that I described to you that's got wallpaper on the wall, the retina, is filled with a clear gel that you may have heard of called the vitreous gel. I spend my career taking that out of people. God knows why. But the vitreous and the retina have areas of traction or interaction, an interface, if you will, that causes a lot of disease. And we can look at the vitreoretinal interface on the OCT here in a very diseased eye. And so we have a very nice way of looking at that interface over time. We also have something called fluorescein angiography, which we inject sodium fluorescein into the retinal vessels. It stains the retinal vessels and capillaries white and allows us to assess retinal and choroidal vascular perfusion in a very precise way. You'll keep a memory of this eye because this is one of the first patients, in fact, the first patient that we transplanted. We also have another more functional way of imaging the retinal pigment epithelium called autofluorescence imaging. And what autofluorescence imaging does is it turns out that one of the metabolic products of the visual cycle contribute, or many of them, but one in particular contributes to an autofluorescence signal. So when you shine a light in the back of the eye with certain filters, the eye will fluoresce, the retinal pigment epithelium will fluoresce normally about like this, abnormally hyperfluorescent like this, and when there's no autofluorescence like this, it means the photoreceptors are gone and no longer shedding, and or the retinal pigment epithelium is gone. So normal, hyper is on the way to badness, the metabolites are starting to build up, and black is pretty much dead. And in fact, we can track this over time. This is from a friend of mine, Frank Holtz's paper. We were fellows together a long time ago. And what he did very carefully was he showed that hyper-autofluorescence around this ring of atrophy. Here's the normal picture of this eye, optic nerve, patch of RPE loss here. In the autofluorescence image, there's normal autofluorescence, there's hyper-autofluorescence, and there's lost autofluorescence. And it can predict where these areas of atrophy are going to come over time. Functional imaging. So, normal, AMD, first transplanted AMD, age-related macular degeneration patient, autofluorescence image. Stargardt's, first Stargardt's. So, very compromised, the whole back of the eye, missing, pretty compromised here, missing. Hence their very low vision. Now, we're also collaborating with a group at UC Berkeley, Austin Roorda and Brandon Lujan, and they are working on an adaptive optic scanning laser ophthalmoscope. And we've taken some of our patients and taken them up to Berkeley, and we can image actual photoreceptors, cones, in humans with macular disease. So we can go through and look at these areas with a black and white photograph, and then take this yellow spot here, and look, these are the cones. That is a human cone array in the fovea, and that's fixation, preferred retinal locus. So extraordinary capacity to look at different areas of cones in humans with disease. So we're looking at doing this before and after treatment. These patients have to be able to fixate. They have to have central vision and be able to sit still for a while, which our current patients don't. But as we get into better vision in our patients, we can really do some amazing things. Now, I am hoping that I can start this video by doing that. Maybe that, please. This is such a great video, it's worth trying. This is an ALSLO video. Oh well, sorry. This is the video, this is this area here, you can see this vessel, and basically what it does is the scanning laser ophthalmoscope with adaptive optics focuses up and down through all the layers of the retina. And you'll have to see it next time, I apologize. So that's why the eye. How about why the RPE? Well, the RPE is a critical cell line for vision. It's highly differentiated, it's non-synaptic, so you don't need to put these in there and then have them hook up to something. They just need to be there. RPE loss is a final common feature of important causes of blindness, and I'll go through that, and it's a surgically accessible space. So degeneration of the RPE, as Bob mentioned, leads to photoreceptor loss. Two causes, leading causes of adult and juvenile blindness are dry age-related macular degeneration and Stargardt's macular dystrophy. I'm going to take you through these really quickly. The RPE is important for a lot of reasons, one of which is that it recycles the photopigments in the visual cycle. When there's an abnormality here, which happens in most patients with Stargardt's, the toxic chromophores build up, and in the outer segments they're shed into the photoreceptors, into the RPE. The RPE engulfs them, but it's really a poison pill. Over time the RPE is lost. And so our idea was, and Brooks membrane is relatively healthy in these patients, so our idea was maybe we could replace the RPE and give these patients theoretically a couple more decades of vision. It does not address the underlying molecular biology of Stargardt's, but you know, neither does penicillin for appendicitis, right? And so the RPE does lots of other things. In fact, there are entire textbooks just on the RPE. This is a slide from Dean Bach and Richard Young, work that was originally done at Schwartz Eye Institute many years ago, describing how the outer segments of the rods and cones interdigitate into the apical surface of retinal pigment epithelium and are then engulfed, and the visual cycle happens right here. This is the visual cycle, right? Light comes in, hits rhodopsin, that's with 11 cis retinal. It releases, there's a neural image, and all trans retinal is released, and then it becomes all trans retinal, is shed, engulfed in the RPE, fixed up again, and here comes the cis retinal back. It's complex, but if there's a block right here and that builds up, you get a disease like, this is the ABCR, you get a disease called Stargardt's, and that interferes with vision. Now, that's at the apical end of the RPE. On the back side of the RPE, in this cartoon, you see the photoreceptors, the RPE, and the choriocapillaris with Brooks membrane right here. In age-related macular degeneration, one of two things can happen.